shall study about grammar systems. What is the motivation for this? Today, the idea of distributed computing plays an important role. Different problems of high intensity computation time, they are processed using distributed computing and parallel computing. So, how do you abstract these models? So, from a formal language theory point of view, this was modeled using the idea of a grammar system. In classical formal language theory, a language is generated by a single grammar or accepted by a single automaton. But in a grammar system, several grammars join together and generate a string, and in the automata, several automata join together and process a string. So, single grammar corresponds to a single processor, they are centralized, you can say them, they are centralized. But in distributed computing, you have several processes and the processes are all communicating with each other. How do you capture this with the idea of a grammar or a grammar system? That is what we are going to study today. So, in grammar systems, we have two models, the blackboard model which is a sequential model and the classroom model which is a parallel model. What is a blackboard model or a sequential model? You have a problem to be solved and the students are going to solve that in a class. There is a blackboard. One student comes and writes something on the board, he solves part of the problem, he goes back, the second student comes and continues with the solution, tries to work out a few more steps and then he goes back, then the third student comes, he tries to work a few more steps and so on. This continues until the whole problem is solved. So, the idea is that of a sequential processing, all the students do not solve the problem simultaneously, one by one they come and solve the problem, a portion of the problem and then the next student takes over. So, that is why this is called a blackboard model. So, let us see how it works. The first student goes and he writes something on the blackboard, he comes back. Then the second student goes, he continues with the solution, writes a few more steps, comes back. Then the third student goes, continues with the solution, he comes back and then it is continued with the next student. So, this type of a model is called the sequential model or the blackboard model. The grammars one by one they generate the sentential form and ultimately lead to the string generated. In contrast to that, you have the classroom model. In classroom model, what happens is, it is like a program, you have a main program and in the main program you have subroutines. Each student is given one portion of the program and they have to find the routine, they have to write down the solution for that particular routine. And the main class leader, he is the main person, he is writing the main program or trying the main solution. So, when he executes, he wants some answer, at some point he has to make a function call, it is or a subroutine call. At that stage, he makes a query and the subroutine corresponds to the problem solved by another student and she or he provides the corresponding answer to that. This sort of a processing goes on until the whole problem is solved. So, let us see how this works. Each student is trying to work out some portion of the problem and then this person gets a query, this answer is provided by this person. After some instance, this is the class leader, he is trying with the solution, and he may get another query for which the answer may come from this person. It is like making a subroutine call. This person, when he calls a subroutine, the answer is given here, then he makes another query, the answer comes from here, and this person himself, he may ask for a query, and then the answer may be supplied by this person. So, this sort of a thing may continue, and this sort of a thing is called a parallel model, because all of them are working on their sub problem simultaneously, and one person has a query means he asks and the another person provides the answer. This is called the parallel communicating model or the classroom model. So, let us see the formal definition now. So, the first model is called CD grammar systems or cooperative distributed grammar systems. The definition is like this: a CD grammar system of degree n is a construct GS n T S P1 P2 Pn, where n is the set of non-terminals, T is the set of terminals, S is the start symbol, and P1 P2 Pn are n sets of productions. They are finite sets of rewriting rules over n union T. You can have them as type 0, type 1, type 2 or type 3, or you can also specify the grammar system like this: n T S G1 G2 Gn, where each grammar G I is specified like this. You have the set of non-terminals, you have the set of terminals for each grammar, and you have the start symbol S, and the set of productions are given by Pi for Gi. Either way it can be specified. It is easier to specify this way, we can specify this way also, does not matter. Let G of S is equal to n T S P1 P2 Pn be a CD grammar. CD stands for cooperative distributed grammar system. We now define different protocols of cooperation. What do you mean by different protocols of cooperation? Now, we have seen that CD grammar corresponds to blackboard model. One student works out a few steps and then he goes back, then the next student comes. Now, the question is, at what time does the first student go back and the second student comes? And at what time does the second student go back and the third student comes? There can be several protocols for that. One is any time the student can go back and the next student can come in. That is called the star mode in the formal definition. Another thing is, a student proceeds as much as possible, that is, he is trying to work out a solution and he proceeds till at a certain stage he is not able to proceed further. Then at that stage he goes back and the next student who is capable of proceeding further comes and takes over. And this is called the terminating mode, because the first student spends time on the board as long as possible and goes back only when it is not possible for him to proceed, and the next student comes. In formal model, this is called the T mode or the terminating mode. There are other modes. Let k be a finite integer, and when that finite integer is there, the first student comes and he works out for k steps. In the solution, he continues for k steps, then he goes back. Whether he is able to proceed or whether he is not able to proceed, he just goes back, and then the second student comes and continues with the next k steps. So, each student spends exactly k steps on the board, that is, he writes just k steps on the board and then he goes back. This is called the equal to k mode for k is equal to 1, 2, 3, etc. Then you have what is known as greater to or equal to k mode, less than or equal to k, mode. So, let me write down the modes. We have seen what is the star mode. Anytime the student can go back. T mode, the student goes back when he is not able to proceed. Equal to K mode, these are all modes. Each student writes K steps, and greater than or equal to K mode, each student spends K or more steps on the board. That is, he comes and works for K steps. He may continue for some more steps, but minimum is K. So, minimum K steps, but it can be more also, then he goes back, the next person comes and so on. Similarly, you also have less than or equal to K mode, that is, each student spends K or less number of steps on the board. He can start 1 step or 2 steps, up to K steps he can go, but he cannot go beyond that. So, you have 5 modes of cooperation in this grammar. The star mode is called the normal mode, and the definition of derivation is like this. Normal mode, the ith component, it is defined by from x you can derive y without any restriction. Any number of steps you can spend on the ith component, or the ith grammar you can have a derivation any number of steps. In a naive manner, when you say, the student works on the blackboard as long as he wants. Terminating mode, for each I belonging to 1 to n, the terminating derivation by the ith component, that is denoted by the symbol double arrow. This denotes the component in which the processing is done. T denotes the terminating mode, that is defined like this, that is, you are able to derive from x the string y, and from y you cannot proceed in the same component, that is, there is no z such that from y you can derive z. Then this is called the terminating mode. Then you have the equal to mode, equal to K mode. K is an integer, I denotes the component number. The K steps derivation by the ith component is denoted by this. From x you can derive y in this if you have x1, x2, xk plus 1, where x is equal to x1, y is equal to xk plus 1, and from x1 you can derive x2 in one step, x2 from x2 you can derive x3 and so on. In general, from xj you can derive xj plus 1. So, you have k steps deriving x2 from x1, x3 from x2, x4 from x3 and so on. So, in k steps you derive xk plus 1 from x1, and all of them take place in the same component pi. And less than or equal to K mode, you have K or less than or number of steps, that is, x less than or equal to Ky if and only if it is done in K dash number of steps, where K dash is less than or equal to K. And similarly, greater than or equal to K mode, that is, you derive y from x in greater than or equal to K mode in the component pi if you derive y from x in K dash number of steps, where K dash is greater than or equal to K. So, these are the modes, and so the mode you can denote as D is equal to star T star. You can have the star mode, you can have the T mode, you can have the less than or equal to K, greater than or equal to K, equal to K mode, where K can be an integer, it can be 1, 2, 3, etc. The language generated by the grammar system with n components in the mode F, F belongs to D. We have seen what is D earlier. It is L of f g of s is equal to a terminal string which belongs to T star, such that from S you derive the sentential form alpha 1 in component I 1, in the F mode, and from alpha 1 you derive the sentential form alpha 2 in component I 2 in the same mode. Proceeding like this, you derive alpha m from alpha m minus 1 in component I m using the same mode. So, m is greater than or equal to 1, and these are all one of the n components. So, each I j is between 1 and n, it is one of the components. After case, if it is equal to k mode, after k steps it has to switch component. Similarly, if it is a T mode, when it is not able to proceed further, it switches component. Let us consider some example. Consider the following CD grammar system, where you have these are the non terminals S, X, X dash, Y, Y dash, terminals are A, B, C. S is the start symbol. You have two components. In one component you have these set of rules, the other component you have these sets. So, these are the rules in the first component, in the second component you have the following set. Now, what is the language generated under different modes? Suppose you consider the star mode, any time you can switch from one component to another. You have to start the derivation with S. So, S goes to S, you can use any number of times you want, then you have to go from S to X y. Now, when you go to X y, you cannot proceed in this component because there is no rule with X on the left hand side or Y on the left hand side here, and you have to use either this or this. Now, if you use this in the star mode, after one step again you can come back here. If you use this, again you can come back here, or you can use both and come back here. Then X dash and Y dash can be turned into X and Y. You can just turn one of them and again go back, or turn both of them and go back. All possibilities exist. Because of that, you find that this rule along with X dash goes to X will generate number of A's. So, one A will be generated, again you can repeat this process any number of times. So, as many A's as you want you can generate. Similarly, you can use this rule and again change Y dash to Y and then use this rule any number of times you want. So, with this sort of a thing, any number equal number of A's and B's will be equal number of B's and C's will be generated, and that can be done any number of times. Finally, you end up the derivation with this rule or with this rule. Both X and Y have to become terminals. As long as there is one non terminal, the derivation continues. So, in the sentential form, you will have either X dash or Y dash or both, or X or Y or both. You can have X dash and Y or X and Y dash and so on. So, it is possible to derive any number of A's and any number of B's and C's, but the number of B's and C's will be equal because this is a linear rule. So, the language generated will be equal number of B's and C's and any number of A's. Of course, there is no connection between M and N except that they are greater than or equal to 1. So, the same idea you can also consider for T mode equal to 1 mode, greater than or equal to mode, less than or equal to K mode, etc. But if you consider the equal to 2 mode, there is a difference. So, if I consider equal to 2 mode, in each component there should be 2 steps taking place. So, what you have is you start here one step, second step. So, X and Y you have, and now you switch to the next component, and the next component you have this rule and this rule. So, when you have this rule, one A is generated. When you apply this rule, 2 steps have to be performed in this component, and the only way you can do is this and this. So, one A will be generated, one B will be generated, one C will be generated. Now, after applying 2 steps, you go back to the first component, change the x dash to x, y dash to y. So, 2 steps are over here, come back, again generate 1a, 1b and 1c, go back and so on. This you can continue, and every time you come to the second component, 1a, 1b and 1c will be generated, and when you go to the first component, x dash and x y dash will be changed into x and y. Finally, you have to terminate the derivation with this rule and with this rule. If you use just one of them and go back, there will be problem. What is the problem? You are spending only one rule here and it is not possible, you have to use 2 rules. So, when you want to use this rule, and then if suppose you use this rule and go back here, you can use only one rule, and that is not allowed. You have to use 2 rules in each component. So, when you have equal to 2 mode, the language generated will be a power n, b power n, c power n, which is a context sensitive language. Now, the rules in each component can be type 0, type 1, type 2 or type 3, but of interest is type 2, because when you have context free rules, the power is increased. You are able to generate context sensitive languages with context free rules in a grammar system. Whereas, if you use just type 3 grammar regular rules, then the power will not really be increased. You will be able to get only regular sets. Now, suppose k is greater than or equal to k mode or greater than or equal to mode you consider, where k will be 3, 4 or 5. Then look at the rules. Here I can have only 2 steps, I cannot have more than 2 steps. So, if it is equal to k or greater than or equal to k mode, where k is 3, 4 or 5 or etc., no derivation is possible, the language generated is empty. Another grammar, let us look into this. So, this is a grammar with 3 components. There are 2 non-terminals, 1 terminal and 3 components. The rules are like this. In the star mode, you can use this rule, and then again you can make it go into this, you can generate a, any time you can convert the a into a small a or convert it into s and generate 2 more a's, and you can see that you can generate 2 a's, because first time you have to use this rule. 1 a it is not possible to generate, it is possible to generate 2 a's or 3 a's and so on. So, the language generated will be this a power n, n greater than or equal to 2, which is a regular set. Now, similar result holds for equal to 1 great equal to k and so on. What is the language generated in the T mode? Okay. If you have greater than or equal to k, k greater than or equal to 2, then the language generated is empty, as this can be used only once in P1 and a goes to a can be used only once in P3 for the equal to 1 mode. Now, in the T mode, what is the language generated? Go back, S goes to a, then suppose I start using this rule, then I have to convert both the a's into s's. Then I go back here, then both the s's I have to convert into a. So, I will get 4 a's. So, the derivation will be like this. Either I will get 2a and the a's can be converted into small a's, where I will get a squared, or they will get converted to s's, and again I use the rule s goes to a. It is a terminating mode, I should proceed in the same component as long as possible. So, again this s also will be converted into 2a. Now, I have a chance to go to component 3, where all the 4 a's will be converted into small a's. It is not possible to just convert portion of it and leave the other, because it is a terminating mode. As long as it is possible to apply the rule a goes to a, I will have to use it. Then if I use the rule a goes to s, all the 4 a's will be converted into 4 s's, and so 4 s's will be there, they will be converted into 8 a's using the first component, and again I have the choice of making them into small a's or proceeding further. So, you will find that you can generate a power 4, you can generate a squared, you can generate a power 8 and so on. So, the language generated in the T mode is a power 2 power n. Another grammar let us consider, this also has 3 components. The first component has rules like this, the second component has rules like this and so on. There are 3 non-terminals, 2 terminals and so on. What happens when you have star mode equal to 1 mode less than or equal to k mode? So, you have to apply this rule to proceed further. Then I can just proceed with this x1 in the star mode and generate something I want, turning into x2 and then again going back to x1, going back here and so on, anything I can derive. So, from x1 I can derive some string of a's and b's. I can do the same thing with this x1, have derive some string from the second x1. So, I can really derive 2 different strings from the 2 x1s, but minimum is 1 symbol. So, the length of the string will be generated, the length of the string generated will be greater than or equal to 2. Minimum length is 2 and actually W will be of the form W1, W2, where W1 and W2 are any strings of A's and B's. So, that is why you just have any string of A's and B's generated where the length of the string will be minimum 2, it can be anything. But what happens when you use equal to 2 mode? So, at each component you have to use 2 steps. The derivation in each component consists of 2 steps. In that case, what happens? You use 2 steps, s goes to s, s goes to x1. Now, from this x1 if I use this rule and from the second x1 if I use this rule, I can derive 1a and 1a, but if I go here x2 can be converted into x1, but here I have to spend 2 steps, right, that is not possible. So, if I use this rule for this x1, I have to use the same rule for this x1. Okay. So, the derivation will be like this. In the first component starting with s, I get s in one step. Actually the rule s goes to s is just added so that you are able to get 2 steps in the first component. Then from this you get x1, this is done in 2 steps. Then you have to go to another component. If you go to P2 and apply the rule, you will get a x1. You have to use the same rule here, a x2, right, a x2, a x2. Then you go back to the first component and convert this into a x2 into x1, x2 into x1. So, from here to here there are 2 steps, this x1 derives this x1 derives this, and here again 2 steps, x2 goes to x1, x2 goes to x1. Then I can proceed using the rule by going to the third component b x2 a, then using the same rule I can get b x2 and so on. Then I can terminate the derivation using something. So, I can get something like a b b. Again note that you are using 2 rules in each component. Suppose at this stage I try to use b x2 here, but just b here. What happens? When I go to the first component to convert x2 to x1, I can use only one step, and that is not allowed. I have to use 2 steps. So, when I use the rule, it has to be repeated twice, and I get strings of the form w, w. We know that this is a context sensitive language, but note that each component has only context free rules. So, with context free rules you are able to generate context sensitive languages. In fact, the 3 languages A power n, B power n, C power n, WW, and A power n, B power m, A power n, B power m, they are called they have some features, they are useful for defining what is known as mildly context sensitive languages. And usually when you consider a context sensitive language means usually consider these 3 languages and show that they can be generated. Of course, A power n square does not come under this. Okay. Now, what can you say about the generative power? It is very interesting that context free rules, with context free rules you are able to generate context sensitive languages, but what happens if you use type 0 or type 1 rules? Actually type 0 or type 1, it can be seen that the CD grammar systems working in any of the modes, it can be star mode, T mode or anything, but if you have regular rules or linear rules or context sensitive rules or type 0 rules, then the generative power does not change, it does not increase. Whatever you can do with n components, you can just do with one component. You can rewrite the rules in such a way that you achieve the same thing with one component. They generate the families of regular, linear, context sensitive and recursively enumerable languages. The power is not increased, whereas when you use context free rules, the power is increased. So, this is seen by the examples which you have just now seen. By the examples given, we find that the CD grammar systems with context free components can generate context sensitive languages. If you denote by CDNF, the family of languages generated by CD grammar systems with epsilon free context free rules and n maximum n components, then you also denote by CD infinity f if you do not put a restriction on the number of components. And if you are allowing epsilon rules, you also use this and this, and there are several results related to their power. We will not go into the details of them. Now, let us come back to the other model, PC grammar systems, or this is called parallel communicating grammar systems or the classroom model. So, what happens here is you have a set of non-terminals, the formal definition is this. You have a set of non-terminals, you have a set of terminals, and you have another set which is called the set of query symbols. If there are n components, you have n query symbols, and corresponding to each component you have a start symbol, you have a set of predictions, start symbol, a set of predictions, and so on. Now, in this you have n components. So, there are n start symbols and n production sets. Now, without loss of generality, we assume n, t, k are all mutually disjoint, and the total alphabet is denoted by n union k union t, and we denote it as VGP is n union k union t. The sets Pi are called the components of the system. The index I for Qi, Qi is the query symbol for the ith component. So, when Qi appears, the answer has to be provided by the ith component. The equivalent representation is also like this. Instead of P1, P2, Pn, S1, P1, S2, P2, Sn, Pn, you can also have G1, G2, Gn, where Gi is n union k t Si Pi. Given a PC grammar system like this, how do you define derivation in this case? So, you have n strings, and from this is an ID, instantaneous description, it consists of n strings. From this the next ID is y1, y2, yn. How do you get this? There are two steps, two different types of steps you can use. One is the actual derivation, another is the communicating step. Now, there are two possibilities. Here none of the xi's contain the query symbol. This tells you that xi does not contain any query symbol, no query symbol in xi, and then there is a non-terminal. If there is a non-terminal, you can use a derivation step and get yi from xi. If there is no non-terminal, it is only a terminal string, you have to keep it as it is. The other one is the communication step, that is xi has a query symbol. This denotes that, this sort of a notation denotes that xi has a query symbol. In that case, suppose xi is like this: z1 qi1, z2 qi2, zt qit, zt I plus 1, where z1, z2 they do not contain any query symbols. The query symbols appearing in xi are qi1, qi2, qir. Then what happens is, the next stage xi is replaced by putting the value of the corresponding string in the i1th component here, the corresponding string in the i2th component here, corresponding string in the itth component here, and you get yi. So, the yi will be zi, xi1, z2, etc. z1, z2, zt, zt plus 1 remain as they are, but the query symbols are replaced by the strings provided by the corresponding components. Now, after this is done, from xi you have got yi in the ith component. What happens for the ijth component? The i1th component provides this string to the ith component, the i2th component provides this string for the ith component, but what happens to them? What happens to the ijth component? It starts again, once again it starts from sj, that is called the returning mode. So, it returns the start symbol. In the non-returning mode, it keeps the corresponding string xij as it is and proceeds further. Let us see one example, and this is achievable only if these strings do not contain query symbols. If they have query symbols, there will be problem, you cannot do this. So, you have an instantaneous description like this. So, an ID is a n tuple like this, each is a string over the total alphabet, and it can give rise to the next ID y1, y2, yn. If you can have component wise derivation, that is no query symbol is there, from x1 you derive y1, from x2 you derive y2 and so on. Each xi has a non-terminal. If there is no non-terminal, it is a terminal string, you keep it as it is. So, you either use this rule or you keep it as it is. Then you have the communication step. In the communication step, you have query symbols. Suppose qj appears in xj, then qj will be replaced by xj, provided xj does not contain any query symbol. In essence, the component xi contains query symbols is modified only when all occurrences of the query symbols in it refer to strings without the occurrence of the query symbols. The communicating step, xj replaces the query symbol qj. After that, the system resumes starting from the axiom, that is the jth component goes back to the start symbol, means it is called the returning mode, or if it continues from where it was, it is called a non-returning mode. And always communication has priority over rewriting. Only when there is no more communication possible, you will use the derivation step. But there should not be any circular question and query symbols. we will see what is a circular query symbol. Now, you may not be able to replace xj by the corresponding string. Suppose at some stage I have x1, x2, xn, and I also have, say, this has qj, but xj has the symbol qk, say, then I cannot replace it like this. But the kth component, suppose this is the kth component, this is the kth component, this may not contain any symbol. So, first replace this with this, then use this to replace xi, qj in xi. So, this can be done. When it is not possible to do something like that, it is called circular query, and the derivation stops at that stage. If some query symbols in a component cannot be replaced in a given communication step, it may be possible that they can be replaced in the next step. That is what we can do. When the first component is called the master of the system or the centralized system, it has a terminal string. When the first component derives a terminal string, no more derivation takes place, the derivation stops. So, double arrow is used to denote both the rewriting step and the communication steps. As usual, double arrow star is the reflexive transitive closure of double arrow. When you use returning mode, you use R below that. When you use non-returning mode, you use NR below that. The language generated by the PC grammar system in the returning mode is LRGP. The first component derives a terminal string. So, you start with the n tuple S1, S2, Sn, and you arrive at x alpha 2 alpha 3 alpha n. These may be non-terminals or terminals, does not matter, but the first component derives a terminal string. In the non-returning mode, you use the non-returning derivation steps. So, starting from the n tuple S1, S2, Sn, the first component derives a terminal string, and that is the string belonging to the language. If a query symbol is present, rewriting is not possible. So, you have to finish all the query symbols before further rewriting takes place. If a circular query occurs, communication will not be possible and the derivation halts without producing a string for the language. What do you mean by circular query? Component I has qj and j has qk and k component k has qi. So, when it is asking for qj xj, it has qk, and when it is asking for the ith component, it will have qi. So, that way you will never be able to get out of all the query symbols. The first component is called the master of the system, and the language consists of terminal strings derived there. Generally, any component can introduce query symbols. So, you do not put any restriction, any component can generate a query symbol and the corresponding component can give the answer. We saw the several students working in a classroom. Any student can ask a question if he does not have the answer for that, and the student who has the answer for that should produce the answer. This is the non-centralized version. The centralized version, only the class leader is allowed to ask questions. He is proceeding with the main program and main problem or the main program, and when he gets some queries or when he wants the answer for something, he asks the corresponding student who is working that particular portion of the problem, and that student has to provide the answer. Only the leader has the capability of asking questions, or only he is permitted to ask questions, or in the grammar system only the first component can produce query symbols. Such a system is called a centralized system. So, you have centralized, non-centralized, returning, non-returning. So, 4 types of thing you have, 2 into 2, and what is the language generated under different things, that is has been studied. What can the rules be? It can be regular rules, linear rules, context free, context sensitive. What is the class of language generated? What are the properties of them? These are been studied widely in the book. There are book chapters on this. So, let us just consider some examples now. Consider this example. You have 3 components. P1 has these rules. You have S1, P1, S2, P2, S3, P3, 3 components. P1 has a number of rules like this 1, 2, 3, 4, 5, 8 rules. P2 has just 1 rule, P3 has 1 rule. What is the language generated in the returning and the non-returning mode? We will find that the language generated is A power n, B power n, C power n. You can see this S1, S2, S3. There is only one rule, S2 goes to B, S2, S3 goes to C, S3 in these 2 components. So, you have to apply that only. But in component 1 you have 8 rule, you can use any one of them. If you use the first rule, you can use the second rule, you can use any one of them. So, see, if you use the first rule you get this is the terminal string, no further derivation is allowed. So, this belongs to the language, ABC belongs to the language. It can be either returning mode or non-returning mode, does not matter. Similarly, if you use the first rule, you will get A squared, B squared, C squared in the first component. It is both in the returning mode and the non-returning mode, it will be generated. Now, what happens when you use the other rules? Suppose the 4th rule I use here. So, if I use the 4th rule in the first component, A cubed Q2 is generated. Here I can use only one rule, S2 goes to B S2. Here I can use only one rule, S3 goes to C S3. So, what I have is this. Now, a communication steps takes place. Q2 is there, the query symbol. So, the answer has to be provided from here. So, this is shifted here and the returning mode, this becomes S2, this is continuing as CS3. Now, what is the rule for S2? S2 goes to B squared Q3. So, if you use that, S2 goes to B squared Q3, this S2 goes to B S2, S3 goes to C S3, if you use, you get this. Now, at this stage again the query symbol Q3 occurs. So, this will be transferred here. So, when you transfer this, you get A cubed C squared S3. This remains as it is, you go back to S3 here, that is returning mode. In the returning mode you get this. So, A cubed B cubed, then you use the rule S3 goes to C and you get this string. Similarly, you can find that in the non-returning mode also the same type of a derivation takes place, but here the components may be having something else. Okay. So, whatever it is, you can find that A power 4, B power 4, C power 4 also can be generated in the returning mode and in the non-returning mode. So, the language generated is A power n, B power n, C power n. Consider this grammar. This is a PC grammar. There are 2 components. This is one component, this is another component. The rules are given by this. The language generated is of this form W W, because in the first component I always use the rule S1 goes to S1, S1 goes to S1, S1 goes to S1, and in the second component I can use the rule A goes to AS2, A goes to BS2 and so on. Any string I can derive here. Now, once you terminate the derivation here, as long as you can proceed here, you can proceed as much as you want, 1 step, 2 step, 3 step, any number of steps. Once you get a terminal string, you cannot derive anything further here. And from S1, if you use the other rule here is S1 goes to Q1, Q2. it should be Q2 Q2, sorry, it should be Q2 Q2. So, when you generate Q2 Q2 here, there are two query symbols appearing, both of them refer to the second component. So, for this Q2 ABB is supplied, for this Q2 again ABB is supplied. So, you get strings of the form WW here, and because you can use any order of derivation here, any W can be generated. So, the generated string will be of the form WW. In the returning mode this becomes S2, in the non-returning mode it becomes the same thing, I mean it is not disturbed, does not matter, we are only interested in the terminal string generated in the first component. So, the string generated will be of the form WW. So, we have seen how context sensitive languages can be generated using the context free components in all parallel communicating model also. This type of a communication is called communication by request. There is also something known as communication by command. What is communication by request? Because the query is generated, query symbol is generated, QI is generated, then you ask the ith component to provide the answer for that. So, the request is made, and the answer is provided. So, this sort of a communication is called communication by request, whereas there is something called communication by command. What is communication by command? So, each component is deriving some string, and when a particular type of a string occurs, with each component you also attach a set, a regular set, and when that regular set appears, when the string generated belongs to that regular set, something is communicated to the other component. This component at a particular stage, when the string belongs to a set, decides to communicate something from here to another component. So, it is giving a command. So, when something occurs, a command is generated and some string is transferred from this component to another component. Earlier what we considered is a query symbol is generated as a request and something is provided for the query symbol. Here some command is generated here, and when that command is executed, this will be transferred to some other component. And this sort of a communication by command is also very useful. In computer networks, you want to study about the design of the system, you may have clients, you may have servers, and you may want to talk about congestion, how the system can be uniform distribution can be given among the servers, so that one is not overloaded and so on. When you want to study this, first of all it is very essential to study the workload on each server. What type of a workload is generated here? One server may just handle one sort of simple sort of a thing. One client may be just using email, and another client may not communicate with the server at all. Some text processing may just be going on there. So, it is very essential to characterize the workload at each server and then arrive at a scenario where the load will be distributed properly. So, at one stage a few years back, this has been an important study in computer networks, how to characterize the workload. And for that, a parallel communicating grammar describing the behavior of the system, whether it is a client or a server, you can model it with what is known as a parallel grammar, or you can have a context free grammar with probabilities and attribute. So, you can have a CFG, so probabilistic, and also it has attributes. Each client or a server may have such a system, but then you know the whole computer networks describes a distributed environment. So, instead of modeling each one by a separate single context free, probabilistic and attributed system. If you have a parallel communicating system, it gives a very good result. And also the communication method used for that is better, you use communication by command rather than communication by request. So, these models have lot of practical applications. The cooperative distributed model, which is a sequential model, and the parallel model is parallel communicating systems. Again, they have a lot of applications, practical applications, where their use is very well utilized. So, this is another model, another advanced topic which is of current interest.